Okay. So we have derived two equations for two conditions. One is, first condition is what? Both the ends are hinged. Second condition is one end is fixed and another end is free. For that condition we have derived the equation for buckling load or the crippling load. Okay. Now the third condition is, okay, the third condition is, all of you write down. Third one, expression for buckling load or crippling load when both ends of the column are fixed. Okay, we will derive the equation for buckling load when both the ends of the column are fixed. Okay, the procedure behind the derivation is same only, but the end condition is different here. End condition is different. So the boundary conditions which we apply during the derivation process, that will change. That's it. Okay. Whatever the procedure we have followed for previous derivations, no, we have to follow the same procedure here. Okay. But we have to change the formulae or the boundary conditions or the end conditions accordingly with respect to the given condition of the given support condition of the column. Okay. Now consider a column. All of you write with me. Don't simply listen to the class. See, out of all these four derivations, definitely you are going to get one derivation for your external examination. So understand clearly all the derivations. So here it is said that both ends of the column are fixed. Okay, let us take a column of length L. Okay, column of length L fixed at both ends. See, when this column is subjected to the crippling load P or buckling load P, what will be the deflected shape, students? So as the support provided here is, it is a fixed support, then deflected shape will be, see, this support will not allow any movement, either it may be a movement in the x direction or movement in the y direction or the rotation. So there will be reactions exerted in all the ways. Okay, that is for the rotation as well as the displacement of the member in both horizontal and vertical directions. So the deflected shape of the column when it is provided with fixed support at its both of ends will be, I will write it now. So this is the deflected shape, students. Okay, this is the deflected shape. So the reactions or reactive moments will be induced at both the ends of the column. That reactive moment will be, see here at the bottom support, students, how the column is deflected. At the bottom support, the column is deflected in which direction? In clockwise direction. So the reactive moment whatever induced, okay, reactive moment whatever it is induced will be in opposite direction. Opposite direction means in anti-clockwise direction. Okay, that moment we will call it as m naught. Okay, similarly if you take the top support, okay, the deflected shape of the column, how it is deflected? How it is deflected? It is deflected in anti-clockwise direction. So the reactive moment, whatever it is induced, will be in opposite direction. It will be clockwise direction. Moment induced at top support will be in clockwise direction. I hope you all understood how to write the reactive moments at bottom and top support. Depending upon the direction of the rotation at the particular support, you need to write the reactive moment. Okay. So as like previous problems, here also you need to consider a section. Okay. You need to consider, oh shit, just a minute. Okay. Now here also you need to consider a section at a distance x from the support. Consider a section at a distance x from the bottom support. Okay. At a distance x, let y be the displacement. Okay. Let y be the displacement at a distance x. Okay. Consider a section x from bottom support. Let y be the displacement at the section x. Okay. This we have done in the previous derivation. Correct. The same thing we have assumed in the previous two derivations. For all derivations it is the same. We need to assume a section at distance x and we need to assume displacement as y, corresponding displacement at distance x as y. Okay. Is that clear for you all students up to here? Is it clear? Bharat?
Yes.
Okay. Now, as I said, procedure is same. First you need to take the moment at section x, means moment at, I will mark this point as I will mark this point as point D. Okay. I will mark point as point D. Now we will take moment at section x, means moment at the point of the column where you have considered the section. Okay. We will take moment at D, point D, or moment at section x. Okay. Now before that I will write some introduction like let P be the crippling load. Let P be the crippling load. Crippling load or buckling load. All of you do the derivation along with me. All of you should write crippling load or buckling load. For which the column has just buckled. Okay. Okay. Now consider a section x. At section x, let y be the corresponding displacement. Okay. Now taking moment at section, moment taking moment at section X, nothing but moment at D, moment at point D. Okay, what we will get if we take moment of the forces at this point D? Okay, if you take moment of forces at point D, what you will get? What is moment of this force P about point D? I want moment of force P about point D. M is equal to what you will get? See, here we have a clockwise moment. Either we can find the moment from bottom to top or top to bottom, as we as we used to find moment either from the left side of the beam or right side of the beam during support reactions and BMD SFD model which we were learning. Similarly, here also either you have to take moment from the bottom of the column or moment from top of the column. Okay. So in the previous two derivations, we have taken moment from the top, sum of moments of forces from top of the column. So here we follow the same procedure to avoid the confusions. So here we have a clockwise moment, correct? We have a clockwise moment, that is plus m naught. Clockwise means plus m naught. Then we have a crippling load or the buckling force P. Okay, we have to take moment of that force P as well about point D. What is moment of force P about point D? What is moment? Force into perpendicular distance. Force is P. Okay, force is P. What is the perpendicular distance? What is the perpendicular distance, students? You need to respond to the questions which I asked. Okay, whether it may be wrong or right, you need to respond. What is moment of force P about point D? What is moment of force P about point D? Arvinda? Prashant?
Yes, sir.
What is moment of force P about point D? P into perpendicular distance? I want moment of force P about point D. Moment is force into distance. Force is P. What is the perpendicular distance? Tell me.
Why, sir?
Why? It's very simple, no? This is the perpendicular distance of point D from line of action of force P. See, this is the line of action of force P. Here we have the point D. So, y is the perpendicular distance of point D from line of action of force P. Okay. What about the sign? P into y. What about the sign? Plus or minus it is? About point D, force P, whether it is causing clockwise moment or anti-clockwise moment. About point D. See, about point D, the force P is causing the anti-clockwise moment. So the sign is minus. Okay. You can write the sign in other way also. This force is causing the concave bending of the column. Okay. For concave bending of the column, the sign is negative. So plus m naught minus P into y. So we got moment at a distance at a section X. Moment at the section X. Okay. So we have a standard formula for the same moment, but m is equal to what? M is equal to what? EI into d square y by dx square. E at d square y by d square. Same procedure, students. Okay, procedure is same. What we have done in the previous two derivations, we have taken moment at section x. Okay, we got some equation. and we know the standard equation for the moment, same moment, m is equal to E into d square y by ds square. I am following the same procedure for this derivation as well. You can look into it. Okay, there are some minor differences between each and every derivations. Okay, there are minor differences that you need to remember. Okay, now from both the equations we can write as ei into, okay, ei into d square. Therefore ei into d square y by dx square is equal to m naught minus py, m naught minus py. Okay, now this y terms, okay, y terms you bring it to one side of the equation. Now what I will do, I will take this minus py to the LHS, so it becomes ei into d square y by dx square plus py is equal to m naught, is equal to m naught. Now what is next step, students? What is next step? Dividing the equation, dividing by ei on both sides. Dividing by ei on both sides, what you will get? D square y by dx square, d square y by dx square plus ei gets cancelled, p by ei into y is equal to m naught divided by ei. If we divide the whole equation by ei on both the sides, both LHS and RHS, so this is what the equation you get. Okay, now in the next step what we will do, we will multiply this RHS, that is m naught by ei, by p and dividing by p, multiplying and dividing by p. Okay, so what you will get by doing this, you will get p by ei, p by ei into m naught by p. Okay, I have rewritten this equation as p by ei into m naught by p. Therefore d square y by dx square plus p by ei into y is equal to p by ei into m naught by p. Okay, so y I have multiplied and divided by p for the RHS means we want one constant at the RHS, that is p by ei. Okay, students, the reason behind multiplying and dividing by p to the LHS part of the equation is we want a constant at the RHS, that is we want p by ei. If you want to get p by ei, definitely you should multiply by p, and to balance that we need to divide by p, so that you will get p by ei at the RHS. If you just refer to the previous two derivations, we have p by ei in the RHS. You can see here, students. Okay, you can see here. See in the first derivation you have the 0 constant at the RHS, but in the second equation, second derivation, you have the p by ei as constant. Okay, p by ei as the constant. So whatever the multiplication factor for y will be there, no? Good morning, madam. Writing pad illé bitbidi. Okay, students. So you can see here the P by EI should be there or in the RHS, either or in the RHS 0 should be there to write the solution for that particular equation. Got it? So here you can see in the first derivation where both the ends of the column are hinged. Okay, in this condition you can see that d square by dx square plus P by EI into y is equal to 0. If 0 is there, no problem, we can write this solution. Okay, if you have some constant at the RHS, you should have the constant as this multiplication factor only, P by EI only. That is why you can see that in the second derivation, we have a constant A, and when we divided by EI, we got the P by EI in the RHS. Okay, when you have this P by EI constant, so whatever the multiplication factor of the Y, the same multiplication factor if you have on the RHS, then only it is possible to write the solution for the equation easily. Okay, so that is why what I have done. So I did not get when I divided by EI, I did not get P by EI in the RHS part. That is why I have multiplied and divided by P. I multiplied and divided by T, so that I will get P by EI in the RHS. Now coming to the solution of the differential equation. The solution. All of you understanding, students? Are you understanding?
Yes, sir.
Okay. The solution of the above differential equation is the same solution whatever we have written for the previous two derivations. Okay, the same solution will be there, nothing. Y is equal to what here? C1 cos x root P by EI, C2 sin x root P by EI. Okay, same solution I will write, but plus whatever the multiplication constant for P by EI in the RHS. See here you can see for in the RHS there is no multiplication constant for P by EI, it is 0. So there is no extra term here. It is just C1 cos x root P by EI plus C2 sin x root P by EI. When you take the second derivation, you have a multiplication constant of A. Okay, multiplication constant A as multiplication constant as A for P by EI term. So you can see as a solution of the equation, I have written the same equation plus whatever the multiplication constant for we have for P by EI, that plus A I have written. Okay. In the previous derivation it was 0 plus 0 it is plus 0. It is plus 0 here. Nothing will come because here it is multiplication constant 0. So here for P by EI multiplication constant is A, so plus A. Same equation plus A. Similarly here also solution of the above equation will be same equation, all right. Y is equal to C1 cos same equation, all right. X root P by EI, x root P by EI plus C2 sin x root P by EI plus what, students? Plus what will be the solution now? Plus instead of A what will come here? Instead of A what will come here? Plus what may be the answer, students? Tell me. What may be the answer? Very simple. You refer to the previous solution. See, same equation plus multiplication constant A. Whatever the multiplication constant we have for P by EI, that I have written. Similarly, here what is the multiplication constant here? For P by EI, what is the multiplication constant? What is the multiplication constant? M naught by B. M naught by P is the multiplication constant for P by EI. So plus What will be the solution here? Plus m naught by p. So this is the complete solution for the above differential equation. C1 cos x root p by ei plus C2 sin x root p by ei plus multiplication constant of p by ei, that is m naught by p. So in this equation, multiplication constant for p by ei was a, so plus a, that's it. Here there is no multiplication constant. Okay, here there is no multiplication constant, so plus 0, only this equation, that's it. In this way, you remember, definitely you are not going to do any mistakes. You will not be having any confusions in the examinations for any derivations. Okay, now we got the solution for the equation. It is solution for the displacement of the column at a section x, that is y is equal to c1 cos x root p by I plus c2 sin x root p by I plus m naught by p. You call this as equation number 1. You call this as equation number 1, where c1 and c2 are constants of integration. C1 and C2 are constants of integration, and their values, all of you write, students, and their values. See, if you just listen to the class, you will lose the concentration. That is why keep writing, so that you will have focus on the class. Okay, and their value are obtained So how to obtain the values of constants? From boundary conditions. From boundary conditions. Their values are obtained from boundary conditions. Okay. Now coming to the boundary conditions. This is very important step, students. Boundary conditions. Boundary conditions. You will get a few boundary conditions which will help to solve for this constant C1 and C2. Okay. So in that first boundary condition is, see, you just look into the type of support. Okay. Look into the type of support here at x equal to 0. So here we have considered x as a variable along the height of the column. So when x becomes 0, okay, when x becomes 0 means at this point. What about the displacement, students? What about the displacement y? When x equal to 0, displacement y is also equal to 0. The same condition I will write here, x equal to 0. When x equal to 0 or at x equal to 0, corresponding displacement y equal to 0. And also the slope will be also 0. There is no slope here. Initially this column is straight only. After that, after some distance, there is buckling of the column. So here there is no slope. Okay. So initially it is straight like this. After that it is bent like this. Okay. So slope means what? When you draw a tangent, whatever the angle you get, with respect to the horizontal will be, it will be slope. Okay. But initially there is no slope. It is straight only. This angle is 0 only. So angle with respect to vertical is theta. Okay, angle with respect to vertical is taken as theta. So this angle is 0 only. There is no angle. Slope is also 0. Remember, always for the fixed support, y will also be equal to 0 and slope dy by dx will also be equal to 0. Both terms will be equal to 0 only. Okay, understood students? So here one more condition what we get is dy by dx equal to 0. The slope is also equal to 0. Similarly at x equal to L, at x equal to L, what about the deflection at x equal to L? Means at this point, okay, at x equal to L, when x equal to L, deflection y is 0 and similarly slope is also 0 at the other point, because at there also we have the fixed support. Same condition we get x equal to L, at x equal to L, y equal to 0 and dy by dx equal to 0. Okay, and dy by dx equal to 0. Now we will take each and every conditions one by one and we will solve for the constants. Now I will take first condition at x equal to 0, y equal to 0. Okay, I'll take this first part of the first condition, x equal to 0, at x equal to 0, y is equal to 0. Now we have the equation for y. Substitute x equal to 0 and y equal to 0 in this particular equation 1. So the equation 1 becomes equation 1 becomes y equal to 0, y equal to 0 is equal to c1 cos x, means c1 cos 0, it becomes c1 cos 0 plus c2 sin 0 plus c2 sin 0 plus we have one constant, that is m0 by p. You write as it is, plus m0 by p. Okay, therefore 0 is equal to c1 cos 0. Cos 0 is 1, so c1 plus sin 0 is 0, m0 by p. By this you will get the value of c1. Therefore the c1 is equal to minus m0 by p. Minus m0 by p. Okay, now we got the equation for c1. Okay, now I will take second part of the first equation. When x equal to 0, y equal to 0, I have got the value of c1. Now I will take second part of the first equation, that is when x equal to 0, dy by dx equal to 0. Okay, that condition I will take now. Taking at x equal to 0, corresponding slope dy by dx equal to 0. Taking this condition, what we will get? First we need the value of dy by dx. Okay, we have the equation for y, but we need dy by dx. Therefore differentiate this equation 1 with respect to x. Differentiate equation 1 with respect to x. So on the LHS we have the y, that is dy by dx. It becomes dy by dx is equal to, what is the differentiation of c1 cos x root p by ei? So it becomes minus c1 sin x root p by ei into differentiation of this bracket term. What is differentiation of this bracket term? Only root p by ei into root p by ei plus, now differentiation of c2 sin x root p by ei will be equal to c2 cos x root p by ei into differentiation of this bracket term will be root p by ei plus what is differentiation of this constant m by m naught by b? It will be 0. It will be 0. Now I'll rewrite this equation. Therefore, dy by dx is equal to minus c1 root p by ei into sine of x root p by ei plus c2 into root p by ei into cos x root p by ei. I have rewritten this equation. Now apply the second part of the first equation, that is x equal to when x equal to 0, dy by dx equal to 0, substituting when x equal to 0, dy by dx is equal to 0. So dy by dx equal to 0 plus 0 is equal to minus c1 root p by ei into sine 0 plus c2 root p by ei into cos 0. So sine 0 value is 0, correct? Sine 0 value is 0, so this term becomes 0. Therefore the equation is 0 is equal to cos 0 value is 1. So remaining equation will be c2 root p by ei, correct? c2 root p by ei. Therefore rewriting the equation, c2 root p by ei is equal to 0. Okay, c2 root p by ei is equal to 0. Now from this equation, either c2 may be equal to 0 or root p by ei equal to 0. Okay, from above equation it is clear that either c2 equal to 0 or root p by ei must be equal to 0. Okay, but if you take the practical consideration of the column, there exists some value of force P, there exists some buckling load, that is why the column is buckled. Without this force P, column would not have buckled. Okay, so there exists some value of P and EI are constants. The geometric properties of the column, they are also constant values, they will be there and P will be there. So P, this P by EI value cannot be equal to 0 because from the practical consideration, buckling load should be there for the column to buckle, and E and I are the geometric properties of the column. Wherever we have got some cross section of the column, for that cross section we should have some values for E and I, and there should be some value for buckling load for column to buckle. So this P by EI, root P by EI cannot be equal to 0. Okay, same thing I'll write from but from practical consideration root P by EI cannot be equal to 0. Therefore what we can write? C2 equal to 0. Now we got constants, the values of constants C1 and C2. C1 is equal to minus m naught by P, C2 is equal to 0. Same C1, C2 values we substitute in this equation 1. Okay, substitute in this equation 1. Substitute the values of C1 and C2 in equation 1. C1 is equal to what? C1 is equal to minus m naught by P, C2 equal to 0. So this second term becomes 0. So y equal to what will get? Below, right? Substitute substitute the values of C1 and C2 in equation 1. What you get? Therefore y is equal to C1 cos x root p by is there, it becomes minus m naught by p cos x root p by ei. Okay, plus C2 value is 0, C2 cos x root p by is there plus 0 plus constant m naught by p plus constant m naught by p. Okay, C2 value is 0. Now the final equation is y is equal to minus m naught by p cos x root p by ei plus m naught by p plus m naught by p. Okay, now we got some particular equation. You call this equation as equation number 2. Now we will move on to the second boundary condition. Now first boundary condition is over. Now we will move on to we will take the second boundary condition, that is x at x equal to L, y equal to 0. Okay, at x equal to L, y equal to 0, second boundary condition at x equal to L, y equal to 0. This is the second boundary. We will apply this second boundary condition for this equation 2. Okay, what we have done initially, we have taken the first boundary condition. From first boundary condition we obtained the constants C1 and C2, values of constants C1 and C2. Then we have substituted the values of C1 and C2 in this equation 1. We got a modified equation, that is equation number 2. Okay, now for this modified equation number 2, we will apply the second boundary condition, that is at x equal to L, y equal to 0. Okay, now substitute x equal to L and y equal to 0. So y becomes equal to 0. Y becomes equal to 0 is equal to minus m naught by p cos 0 plus cos L, cos L root p by ei plus m naught by p plus m naught by p. Okay, now I will take this first term to the LHS. It becomes m naught by p cos L root p by ei is equal to plus m naught by p. Okay, now on both LHS and RHS we have m naught by p, so we will cancel that term. What you will get finally? You will get cos L root p by ei is equal to 1. So when you will get cos value as 1, when you will get cos function as 1, when, okay, cos L root p by ei is equal to, when you will get cos function as 1, when cos value is 0 or when cos value is 180 cos 2 pi or cos 4 pi or cos 6 pi and so on. Okay, therefore the L root p by ei must be equal to some constant here. Okay, considering the least practical value, considering least practical value, see the cos pi value is also equal to 0. Cos pi value is also equal to 1, but it is minus 1. That is why cos pi will not come into picture, cos 2 pi will come into picture. Okay, so 360 degree difference we need to write. Okay, so considering the least practical value means this 2 pi will come, because 0 will not come. Okay, so the value of L root P by EI will be equal to 2 pi. Therefore L root P by EI is equal to 2 pi. Okay, now we have almost come to end of the derivation. Squaring on both sides. Squaring on both sides, you will get L square into P by EI is equal to 4 pi square. Okay, therefore P is equal to, expression for P buckling load will be equal to 4 pi square EI divided by L square. This is the final expression for buckling load of the column when both ends are fixed. Okay, students, I hope this derivation is clear for you all. Still, if you have any doubts, you can anytime you can contact me. Okay.